I welcome you all for this presentation. In this presentation, we are going to discuss one of a very famous algorithms, that is Advanced Encryption Standard. The short form is AES. This is the overview of this presentation, introduction, then Rigendal, the AES cipher, then AES encryption, then steps in each round, key expansion, AES decryption, then some of the implementation aspects, followed by summary of this presentation. So we all are familiar about one famous algorithm, that is the DES, and this AES is a replacement of this DES algorithm. So we all are familiar that what are the disadvantages of DES, and now DES is obsolete. And what is the reason for that also you are aware, because you already learned that algorithm. So this AES is a replacement for DES, and why means it has many theoretical attacks, and those attacks can easily break the DES. So, and it has demonstrated exhaustive key search attacks also. Because of the key size, there may be many critics was there, and the designers of the DES algorithm proved that. But in spite of all those things, and due to the technological advancement, this DES is vulnerable to many attacks. That's so now it is obsolete. So, but we are having many variants of DES. That is one such variant is a triple DES. It is more secure, but it is very slow, and it has some small blocks. So, what the United States National Institute of Standards and Technology decided is they announced a call for ciphers in 1997. 1997, they announced a call for ciphers. Once any call for ciphers rise means those who are working on that area, they used to submit the proposals. At that time, many people submitted the proposal, but only 15 candidates' proposals were accepted in June 1998. And among that 15, only 5 were shortlisted in August 1999. Among these 5, one of the algorithm is the Rigendal. Rigendal, that was only named as AES in October 2000. So Rigendal means AES algorithm only, so don't get confused. And it was issued as a standard, FIPS Pub 197 standard in November 2001. So the announcement came in 1997. Then all those process happens, and finally in November 2001, this AES become the standard. So coming to some of the design principles of AES cipher, that is the Rigendal. It was designed by Richmond Damon in Belgium. So they have given the name based on the designers of this algorithm only, Rigendal. And it has 128, 192 and 256 bit keys, and the input is these plain text is a 128 bit data. So based on these numbers, that is this key size, the rounds may vary in the AES algorithm. And in DS, we know that only 16 rounds are there, and it follows Feastal cipher structure. AES is also a block cipher, but it does not follow any Feastal cipher structure. It has its own structure. And it has a 128 bit key. So if 128 bit key is used means we can also call it as AES 128. And based on the key size, we can give the name. Then AES 192 is there. AES 256 is there. So these are the different variants of AES. Let us see. And it is an iterative rather the Feastal cipher, and it processes data as block of 4 columns of 4 bytes. There in the Feastal cipher structure, what we are doing is we are dividing the data into 2 halves, and one half we are performing one computation, and in the other half we are performing other computation. But here it is an iterative procedure. Entire block is used for one computation. So it operates on the entire data block in each round. Mainly it is designed to have resistance against known attacks, the speed and code compactness on many CPUs, and design simplicity. So these are the advantages of AES. Resistance against known attacks, speed and code compactness on many CPUs, and design simplicity. So coming to the architecture of this AES encryption process, this is the base block schematic of the encryption process. So already we have seen the advantage that the design is very simple. So here you look into the plain text is of 16 bytes, that is 128 bits, and this plain text is converted to a state, input state. Input state in the sense it is converted to a matrix. That's it. It is converted to a state. Then that state is passed on to the initial transformation. Here we are performing the round key operation. So here key is involved in that. Then we are having totally, this initial is a pre-round operation actually. And totally we are having 10 rounds, 12 rounds and 14 rounds. See here, totally we are having different rounds based on the size of the key length. 10 rounds if the size of the key length is 16 bytes, and 12 rounds if the size of the key byte is 24 bytes, and 14 rounds if the size of the key length is 32 bytes. So based on the key length, the number of rounds vary. So here, and whatever the number of rounds, up to n minus round, we have to perform 4 transformations, and for the nth round, that is the last round, we have to perform only 3 transformations. So all the output and input are states only. Finally also we are getting a state, and that state is converted to a vector to get the ciphertext. And here we are having the key expansion process. So the key also m bytes we are having, that is also converted to a state, and it is given to the key expansion process, and we are getting different round keys. Round keys also varies based on the round. If it is a 10 round, we are having 10 into 4 bytes, 10 into 4 plus another one for the pre-round we require. So 44 keys are required. Likewise, different number of keys are required, and based on the key size only the round is also decided. And it is not given that why we are having only 10, 12 and 14 rounds. Because the designers have experimented many things, and theoretically also they have proven many things to have fixed this number of rounds. But there is no significance of telling that only with this round, this is the reason for having only this much round. Maybe the security is more, that's why they have fixed this number of rounds. So coming to the AES structure, we are having the data block of 4 columns of 4 bytes. That only we are calling it as a state. What is state means? It is a data block of 4 columns of 4 bytes, and key is expanded to array of words. So here we are having totally 9, 11, 13 rounds in which the state undergoes. Why it is reduced? Because only n minus round only perform 4 transformation. So in order to tell the 4 transformation, only these rounds only have the 4 rounds. That's only this 9, 11 and 13 rounds. But we are having 10 rounds, 12 rounds and 14 rounds. So here you see the byte substitution. It is one S box used on every byte. It is similar to that DES. There we have 8 S boxes. Here we are having only one substitution box only. So based on that we are performing the byte substitution. Next is the shift rows. It is just a permutation, that is transposition type only. Here we are permuting the bytes between groups or columns. Next is the mixed column, that is here we are performing the matrix multiplication on groups. We have already discussed in the finite fields, that is that Galois field. Galois field of 2 power 8 is used in this AES. Then we are having the add round key. Here add round key is also XOR state with the key material only. Here we are viewing as alternative XOR key and the scrambling of the data bytes. So initially we are performing the XOR key material, that is the incomplete last round with the fast XOR, and we are having the table lookup implementation. So these are the gist about the AES structure. So coming to the expanded diagram of both the encryption and decryption of AES. Here in each and every round we are having 4 transformations. So pre-round is there. So in the pre-round we are having only add round key alone is performed. Then all the n-1 rounds perform 4 transformations like substitute bytes, shift rows, mixed columns and add round key. And the last round, nth round, we are not having the mixed columns transformation. And here if you look into means all the 4 transformations, among all the 4 transformations, only the add round key is only using the key. Remaining transformations are not using the key. So if there is no key, there is no security. We mean that. But here what happens means this add round key transformation alone is providing security. Other transformations, what they are doing is they are performing some, giving some confusion and diffusion effect. And with that confusion and diffusion effect, we are adding the round key transformation so that the security is high in this DES. Okay. So then coming to the decryption process, if you look into, it is not exactly the reverse operation, but inverse we are taking, but it is not exactly, the order is not reverse. Here you see substitute by shift rows, mixed columns, add round key. Here we are having inverse mixed columns, add round key, inverse subbytes and inverse shift rows. Different order we are following here. Some comments on the AES, or it is an iterative rather than the feasible cipher, and the key is expanded into array of 32-bit words. So 4 words form the round key in each round. So only for the 10 round architecture we require 44 keys, because for the 10 rounds 4 words plus 44 words are required, that is 4 words form one round. So for the 10 rounds 40, then the pre-round is there, for that we require 4 words. So totally we require 44 words. So 4 different stages are used and as a symbol structure. So now you know that in DS one round is how much complicated. But here one round means only 4 transformations are there, and the transformations are very simple only. So design simplicity is here in this AES. So here the add round key only uses the key, and add round key is a form of Varnam cipher. Varnam cipher we are already aware of, and each stage is easily reversible here. Decryption uses keys in reverse order, but the decryption does not recover the plain text. Final round has only 3 stages. So these are some of the comments on AES. So first transformation is the substitute byte. It is a symbol substitution of each byte, and it uses one table of 16 cross 16 bytes, because here we are following the hexadecimal. So all of you aware what is a hexadecimal? It is a base 16 form, a number system, right? Base 16 in the sense 16 symbols are there, that is 0 to 9 and A to F. So these symbols are only involved in this substitution box also. It is a 16 cross 16 bytes containing a permutation of all 256 8-bit values. So each byte of the state is replaced by the byte indexed by the row, that is the left 4 bits, and the column, that is right 4 bits. That is always we are having 2 digits, 2 hexadecimal numbers we are having. The left 4 bits, left number we have to check it into the row, and right right digit we have to check it into the column. So here if you look into, byte 95 is replaced by byte in row 9 and column 5, which has a value 2A. We will check in the table. And S box is constructed using the defined transformation of values in Galois field of 2 power 8. And it is mainly designed, why this S box is designed means to be resistant to all known attacks. For that only substitute byte is designed. Here next is the example of this. We already have seen that 95. For 95, how you have to look into? For 9, you have to look into the row, and 5, you have to look into the column. So where these values are cross-secting, that is the answer. See here, this is 2A. So this is cross-secting here. So 2A is the answer for 95, whatever the example we have seen there. So here one state is given, and for this state you have to find out the output. So just you have to look into the S box and we can easily get the output. For EA, what you have to look? For E, you have to look into the row, and A, you have to look into the column. So where that is intersecting, it is intersecting here. So it is 87. So EA, it is 87. Likewise, we have to check for all the value and we can get the answer. So substitute byte is very simple. Next transformation is shift rows. So in the shift rows, what we are doing is a circular byte shift in each row we are performing. That is, first row is unchanged, second row does 1 byte circular shift to left, third row does 2 byte circular shift to left, and fourth row does 3 byte circular shift to left. So the decryption inverts using shifts to the right, the reverse process, but it is shift right. Since state is processed by column, this step permutes bytes between the columns. So this is about the shift rows. This is the pictorial representation of the shift row. That is first row we have to take as such. Second row 1 byte of shift, 1 left shift. Third row 2 left shift, and fourth row 3 left shift. See here, first as such it is written 87, 72, 4D and 97. This one shift. So 6C comes here. 6C, then this order. 6C, 4C, 90, then this becomes here. EC. Then here 2 shifts. So here 46 is coming in the beginning. 46, E7, then it goes shifted this side. Likewise we are getting. Then here you see A6 is coming first. 8C, 8995. So this way the shift rows are performed. It is also very simple. The second transformation is also very simple. Then third transformation is of the mixed column. So in the mixed column, what we need to do is we have to multiply the given state with one matrix. This matrix how we are deriving is this is a fixed matrix. Always we have to use this matrix. Only you have to remember the first one, that is 2, 1, 1, 3. Remaining you are performing one shift operation, that's it. So 3 is coming here, then 2, 1, 1. Then again this you are performing shift. Likewise it goes on. So for 1 you have to consider it as 1. And 2 it is considered as x, and 3 you have to consider it as x plus 1 while performing the multiplication. So here always what we are doing is we are performing matrix multiplication in Galois field of 2 power 8 using the prime polynomial m of x equal to x power 8 plus x plus 4, x power 4 plus x cube plus x plus 1. So this Galois field we are applying here. Galois field of 2 power 8 we are applying in AES in the mixed columns transformation. So this is the pictorial representation of that. This matrix already we know. Then we are taking one by one. That is, if you want to multiply, perform this means what you have to do? You have to multiply this by this. This is the matrix multiplication, right? So 2 into 87, then 3 into 60, into plus, instead of plus you have to put XOR operation. This is very, very important, XOR operation. So how you have to do this one? So first what you need to do is, we already seen that for 1 it is 1 and 2 it is x and 3 it is x plus 1. For 87 it is a hexadecimal number, so you have to convert it into binary. So if you are converting it into binary, what happens? 1, 0, 0, 0 and 7 is 0, 1, 1, 1. So this one you have to convert it into the polynomial representation. For 1 it is 1, then we are having x, x square, cube is not there, 4 is not there, 5 is not there, 6 is not there, 7 is there. So x power 7. So x power 7 plus x square plus x plus 1 is this 87. So already what we need to multiply 2 into 87. What is 2? It is x. So we have to multiply with x into x power 7 plus x square plus x plus 1. Then after performing multiplication, you are getting a value, then you have to perform the XOR operation. This is for the first part alone I am telling. Then 3 into 60 you have to convert like this. For each and every value you have to convert like this. General multiplication what we are doing is we have to add it. Here you have to perform XOR operation. That is the only difference. After performing XOR operation, if you convert the result like this, means you are getting the hexadecimal value. So here this AES uses the arithmetic in the finite field, Galois field of 2 power 8 with the irreducible polynomial, this one. So the equivalent of this is this. The equivalent of this value is this. So wherever we are having this value, you have to replace with 1. Other places you have to replace with 0. Or you can call like this also 11b. This way also you can call this one. So always you have to perform mod this 11b you have to perform. So coming to this mixed columns gist, it can express each column as 4 equations and we can derive each new byte in the column. So decryption requires the use of inverse matrix. So always in most of the decryption process, if a matrix is involved means we have to find out the inverse value. So already you are aware how to find out the inverse of a matrix. 3 cross 3 means it is a symbol. 2 cross 2 and 3 cross 3. Beyond that means you have to get the help of the calculator or some other thing. So with larger coefficients, so it is somewhat harder only, and we have alternate characterization also. That is, each column we are having a 4-term polynomial with the coefficients in Galois field of 2 power 8. That is, we are multiplying with the modulo x power 4 plus 1. In order to reduce that hardness, we are going in for this alternate method. Next, last transformation is the add round key. Here it is XOR state with 128 bits of the round key. Again, we are processing it by column only. That is effectively a series of byte operations we are performing. For inverse, that is the decryption, we have to take the inverse since XOR one inverse with the reverse key. So it is also possible here. So here, why this add round key transformation is designed in this sense? It is designed to be as simple as possible for that only. So this add round key is just a form of Vernam cipher on the expanded key only. So it requires other stages for more complexity and security actually. So we are just merging all the 4 transformations in order to give better security. So this is the pictorial representation of the add round key. We are with the state, we are XORing with the word so that we are getting the result. So this is the diagram, that is a hardware diagram or some design of the AES round. We are having a state. From this state we are getting a sub byte, that is substitution byte we are performing. Then the result is again a state. Then we are performing shift rows, the result is a state. Then we are performing mixed columns, the result is a state. Then we are performing add round key, the result is a state. So here whatever the plain text we are having, we have to convert it into a state. Finally, we are getting the result as a state. Then in order to take the ciphertext, we have to convert that state to a ciphertext vector. So coming to the key expansion process, it takes 128 bits, that is 16 byte key, and expands into an array of 44, 52 and 60, 32 bit words, 4 byte words actually. So here you see why 44 means if you are having 10 rounds means also one pre-round is there before the transformation. For that we require 4 words. So only 4, 44, 52, 60. So start by copying key into first 4 words. Then we are loop creating words that depend on the values in the previous and 4 places back. So here we are also performing the XOR only. That is first word in 4 has a rotate plus S box plus XOR round constant on previous before XOR 4th back. So here let us see that how the key expansion is happening. See here we are having a state with respect to this word, the generator is there, it is XORed and we are getting the final word. So this is for the one word creation. That is 4 bytes of 4 bytes we have for one round key, we required 4 bytes. So this is for one round, this is for the next round, likewise it goes on. So the rationale behind this AES is it is designed to resist known attacks, and the design criteria included here is knowing part key insufficient to find many more, because it is also providing avalanche effect. Avalanche effect in the sense if mostly some bit in the plain text changes, half of the bits in the ciphertext, approximately half of the bits. So it is very difficult for the cryptanalyst to find out the plain text. So some part key alone if we know means also it is very difficult to find out the plain text. And it is performing invertible transformation, that is the inverse operation we are performing in the decryption process. And mainly this AES is fast on wide range of CPUs and it uses round constants to break the symmetry. And here diffuse the key bits into round keys, and it is providing enough non-linearity to hinder the analysis, and mainly it is very simple design procedure. So this is the example of the key expansion process. So for each and every 4 bytes or 4 words or 4 words we require here. So for each and every word, what we are doing is we are performing these functions in order to get the next one. Already we have seen in the pictorial representation, likewise it goes on. So if you are having 44 different words we require means these much operations we have to perform. So how difficult to get the key, right? So security, it is providing more security. So this is one example of the encryption process. So in the start of the round, we are having only the round key operation. Then only we are performing all the 4 transformation. So if time permits, you take any one state and try to find out other states and all, or you are getting the answer or not, whatever we learned in the algorithm. So, and it already I told you that AES is providing strong avalanche effect. Here is an example for that. Here see in the 0th round 1 bit is changed and in the first round 20 bits are changed, in the second round 58 bits are changed. Then third round 59 bits are changed, fourth round 61 bits are changed, fifth round 68 bits are changed, sixth round 64 bits are changed. So here the input is 128 bit. So avalanche effect means at least approximately half of the bits has to be changed. That is 64. Here 68 bits have changed in some rounds, and finally we are getting 58 bits are changed. So it is providing strong avalanche effect. So coming to the decryption process, AES decryption is not identical to the encryption in steps done in reverse, but can define an equal and inverse cipher with the steps as for the encryption. But using the inverses of each step with a different key schedule, we have to work on the decryption part. So how it is working means that the result is unchanged when swap byte substitution and shift rows, and swap mixed columns and add round key. So this is the pictorial representation of AES decryption. Already we have seen this. And in coming to the implementation aspect, this AES can be implemented in 8-bit CPU or 32-bit CPU also. So it is efficient in any type of CPU. That is, byte substitution works on bytes using a table of 256 entries. Shift rows is symbol byte shift only. Then add round key works on the byte XOR operation, and mixed column requires matrix multiplication in Galois field of 2 power 8. And coming to the 32-bit CPU, in 32-bit CPU also it can be implemented efficiently. We can redefine the steps to use for 32-bit words. That is, we can pre-compute 4 tables of 256 words. Then each column in each round can be computed using 4 table lookups plus 4 XORs. So the cost of 4 KB to store tables, we can perform or implement this AES in a 32-bit CPU. So the designers believe this is a very efficient implementation and also a key factor in selection as a AES cipher. So only it is called as advanced encryption standard actually. The designers believe that because the Regendal, after that only it was named as AES. So it is the main important thing is advanced encryption standard, and it becomes a standard also, the cipher. So in this presentation, we discuss about the introduction and history of AES, that is Regendal. Then we have discussed about the AES encryption process, the different steps involved in each and every round. That is 4 transformations are involved for up to the n-1th round. And for the nth round, we are having only 3 transformations. Then we discuss about the key expansion process. Then we discuss about the AES decryption process, and we have seen the implementation aspects of AES as also. So it can be used in 8-bit CPU, 32-bit CPU, now 64-bit CPU also it can be implemented. Thank you.